including projects specifically targeted to sustainable and circular aviation. Now, let us now take a closer look to some showcase examples of such projects, starting with MORPHO. And there, Mr. Nazih Mechbal will guide us through these interesting brand new projects where integrated sensors and digital technology are used to benefit the life cycle management of structural components. So Mr. Mechbal is a full professor at the Lab for Process and Engineering in the Mechanics and Materials, and that is at the Conservatoire National des Arts et Métiers in Paris. And he's also responsible for the Dynamic Structure and Control group there. He has more than 18 years experience as a researcher with a well-established position on structural health monitoring and smart structures. And so it's my pleasure to give the floor to Mr. Mechbal, please.
Thank you. Thank you very much. Thank you for Michaela and for all the organizers to give the possibility to give some insight about MORPHO. So MORPHO projects, I'll be quick. MORPHO project, it's about embedded lifecycle management for smart material, but specifically to some parts of the engine. So some background. So I think that the call is very clear. It was next generation multifunctional intelligent airframe with the emphasis on manufacturing, maintenance, and recycling. So what we propose in MORPHO, that I will present you here, just after, is to give a solution to support development of some smart aeronautical engine, specifically fan blades that I will present you, by undoing them with some cognitive capabilities, and also optimize all the manufacturing cycle and the management of the life cycle. So the project is just started in April. So there is no new, how I say, results, but I'm going to give you just a big photo about what we were going to try to do during this 3.5 years that we can. So in MORPHO, what we want to do is to design an innovative, robust, and environmentally friendly industrial process for this type of airframe parts that are multi-material structures, as I will present you. And we are going to give them some intelligence, some smartness by embedded them with some structures from the manufacturing to the recycling. So this is what we call relay on embedded sensors. And this, in parallel, we are going to develop hybrid twins, that I will present, that will follow all the real life cycle of these structures. Okay, so just the consortium. So 10 partners from 6 countries. From here, the coordinator, it's RMIT and SAM, SUSTAINair. And then we have colleagues from TU Delft, Patras University, and then some end user, principally Safran. This is done typically for some airframe parts for the engine from Safran. And we have some from Hofer, one startup, which is Physense, typically for fiber brag. And we have ASI for the parts of helping for the twin, for the digital twin parts of this project. Okay, so what I was talking about, it's about this type of fan blades that is keeping the LEAP engine. It is a famous engine from Safran that is working very well this last years. And this fine blade, it's made from hybrid materials, a leading edge in titanium, and the core in 3D woven composite. And the idea is to work on this fan blade from its manufacturing to its recycling. So the concept, it's a famous circle that we saw it before in the first session of this afternoon. So we go from the design, manufacturing, embedding sensor. This is to do some predictive health management, structural health monitoring. For the manufacturing, this sensor also will be used to automate and optimize the control. And then these sensors will also be used for disassembling, to optimize disassembling, and then see if we reuse or we completely recycle some parts of this smart fan blade. So this cognitive capability will enable us to do some virtuous cycle like that using some digital data. This can be from the hybrid twin and real data coming from the sensors, embedded sensors. So some innovative technology that we hope that we're going to validate is to have some advanced RTM manufacturing. This kind of structures are manufactured with the resin transfer model process. So we propose to embed this process with some specific sensors that will help us to two types of sensors that will be used only to optimize the process, manufacturing process, and sensors that will be used twice. We will have two targets to optimize the process and also to be embedded like the fiber brag sensors embedded in the structure for the life cycle management after. We are going also to work on some printed and electronics sensors that will be printed directly after manufacturing on the structure. Lightweight construction with all the electronic system that will be printed directly on this fan blade. And then with all of these sensors, we are going to develop a hybrid twin. So the hybrid twin, it's just going a little bit more than a digital twin by using some machine learning approach to identify the mismatch between the digital and the real data. So what we know it will be in physical and I will say numerical models, and what we don't know can be identified, can be learned from these sensors with some machine learning approach. So, and this type of hybrid twin, the idea is to work on some reduced model or that can be adapted on the fly using the data provided by the sensors. So there is some work that is that we are doing from this. We began to work on this kind of algorithm and modeling approach. So this is the data, and then to put this this reduced model in some how we say complex system simulation tools that Safran developed, that can then give us some insight on the performances of what's happened on the structures until virtual flight test. So we can put this small model in a complex one, system of system, and then see what's happened. And if in the design we optimize, and we optimize also the impact of this choice on the in-service of the structure. This will be conducted with development of some specific SHM data, probabilistic SHM data driving methodologies based on this this kind of approach, because we are going to work on this fan blade in a rotary test bench to see what's happened and the effect of all these loads on it, and the fatigue test to generate some algorithm that can give some prognostic on the remaining usable life. And finally, if we see that there is some damages that are not that are severe, so then or it's the end of life of the structure. So then we are going to use some two types of recycling technology, two types of technology. Laser induced, it's what we call laser shock, laser pinning. For disassembly, the composite, the part of the titanium from the structure, because the titanium, it's something that is that we want to keep, and then all the parts of the structure can be recycled using some Peoris technologies. So here you have the laser beam that we can generate in the layers some delaminations, controlled delamination directly. Okay, so here you have some outcomes that we hope are going to satisfy from the design, production, performance, and recovery, disassembling. We hope 100% recovery of, let's say, FRP from PCM. Be back to the design, because if we have something that can be can have some functionality to track its health, so we can then, I think, be back to the design and have some damage tolerant design instead of safe life design, which is now the case. That's all. I think just wrap up here what we want to do. Have environmentally friendly manufacturing, recycling, push industry in the line with Europe Commission circular economy, disassembly of the hybrid material, give some new process to help the disassembly of hybrid materials. Competitive cost in the line with the concept of circular economy. Thank you. Brief.
Thank you very much, Mr. Mechbal, for this insight into, I would say, Industry 4.0 technology.
Yes.
And the applications into smart structures.